Hello. Inspired by Ben Eder's great video series about building an 8-bit breadboard computer, I built my own version. I made some enhancements to his build. In this video, I want to talk about the PS2 controller interface that allows me to connect the keyboard to my computer. Today's keyboards are usually connected to the computer through a USB bus, but about 25 years ago, the majority of keyboards had a PS2 connector. That PS2 bus is also a serial bit transfer protocol, and it is a point-to-point bus, so that there is only a single device on the bus. And that bus is device controlled, meaning that the device, in this case the keyboard, generates the clock and decides who's talking on the bus and who's listening. There are two main device types for that PS2 bus. Typically, there are keyboards and mice connected with a PS2 connector. In my case, so that what I gonna tell you today, there is only a keyboard connected. The PS2 bus consists of 4 lines. 2 of them are power and ground, and the third is the clock line, which is a serial clock, which is, as I already told, device driven, so the device generates the clock. And that clock is used for both directions, so whether the host is receiving or sending data, the clock is generated by the keyboard. So there is 1 bit per tick, and this bit is transferred via that data line, that is the 4th line of that protocol. And the line can be driven from either side, so either the host or the keyboard can put data on that data line. The data and clock lines are so-called open collector lines, so the lines are pulled up by default. That is the reason for what I drew those 2 resistors in here. And the line can be pulled down on either side to ground. For the most common direction, data that is sent from the device to the host, clock line low means the data bit on the data line is valid, and the clock ticks at about 13 kHz. It is in the range of 10 to 16 kHz, but typically it's 13 kHz. So I set up my oscilloscope and recorded the transfer of a byte from the keyboard to my PS2 controller, and there are 11 clock ticks for each byte. The first clock tick is a start bit that is always 0. Then there are 8 data bits starting with the first bit, and then comes the next bit, and so on until a complete byte is transferred. The highest bit, bit 7, is transferred last. And these 8 bits make up a byte, whereas the byte is to be read backwards because the most significant bit is sent last. In this case, it is the scan code 4D, which is the scan code of the P key. After the byte is transferred, an additional parity bit is put on the line, which is odd parity, meaning that the number of ones, including the parity bit, must be odd. And finally, there is a stop bit, which is always 1, and that stop bit is also put on the line as a normal bit. The keyboard byte is a key-dependent scan code, meaning that is not the ASCII code of P or any other code, but so-called scan code, and it is dependent on the keyboard layout. So there must be some kind of translation, and that translation must also include the fact that there are make and break codes, meaning that pushing the key sends 1 byte and release set of bytes, and there are even keys that send more than 1 scan code at a time. All that translation between the scan codes and the characters is done in software in my implementation. Receiving a byte must be independent of the CPU clock because the device might send data at any time and we don't know what the CPU is doing right now. And since the byte is divided into single bits, or shift register is needed that shifts all the incoming bits to its right position on each clock tick. The bits themselves are picked up from the data line, and I use shift register 74HC595 that has a serial in line that synchronously shifts every clock tick all the bits that are already in that register to the right and loads the next bit into the least significant position. It also has a parallel output so that a byte that is shifted in can be read at one point at time. But more interesting, it has a separate 8-bit storage output register so that you can pick the byte at any time while the shifting continues and copy that value of the byte to a separate output register. And that output register has a 3-state output, which means it has an output enable line, allowing it to directly be connected to a bus. The device always sends 11 bits for a byte, and so I need to count the incoming bits. I do this with a counter 191, which is a 4-bit counter, so it has 4 output bits that make the numbers from 0 to 15, and it is synchronously clocked, but it has the ability to be asynchronously preloaded so that without having a clock line, you can load any value into that counter. I use one counter and one shift register that allows me to load a complete byte if I ignore the start bit so that I don't put the start bit anywhere. I don't store the parity bit anywhere, and I ignore the stop bit at all. So I just count to 11 and say if I have 11 bits, the byte is completely received. While counting the incoming bits, the byte is fully received after 9 ticks. So after the start bit and the 8 data bits are through, I copy the content of the shift register into the storage register. Then I count another 2 bits, which is the parity bit and the stop bit, and then I reset the counter. So after 11 ticks, the counter is reset to the start value again. One thing to note is that I start counting at counter value 2. That means the byte is received if the counter is at value 11, and the counter is restarted if the counter value has 13. Reason for that is it is quite simple to detect these values with a triple input NAND gate, which is the 74HCT10, which has 2 of these NAND gates on the die. And this NAND gate outputs 0 when all 3 inputs are 1. And so this is a simple method to check for 3 ones. Interesting thing is that number 11 has 3 ones in its binary representation, as well as the number 13 has 3 ones in its binary representation. And the only other binary number that has bit 0 and bit 3 set and has another 1 in the middle is the number 15, and we will never reach that number 15 because we reset the counter as soon as we reach number 13. So that NAND gate with triple input is capable to detect numbers 11 and 13 with no further chips needed. These 3 chips already allow the receive of a single byte from the keyboard, and I go into a bit more details in this schematic. So just a first quick view in the schematic for the PS2 controller. You see the PS2 connector itself is here on the left hand side, and beneath the ground and 5-volt lines there is the data line and the clock line. This clock line is driven by the device, maybe the keyboard or the mouse if you have one, and this clock line is fed through to the counter chip. This is the 191, and to the shift register, the 595, and that shifts in that data bit that is coming from the device, and it is also fed into that shift register. The counter chip counts every single bit that is transferred and will find the numbers 11 and 13 with these two triple input NAND gates that, in case of the 11th bit, will clock that shift register to take the output, and on number 13 will reload the counter with the value of 1. So I told before we have a value of 2 as the starter, and I will tell in a few minutes where that second tick comes from, so that the counter always starts at 2. If a byte is received that is stored in the output register of that 595 chip and can be read by pulling the keyboard enable control line low, and that byte will be sent to the data bus, which is the connector here on the left hand side, D0 to D7, and since the least significant bit is sent first, that bit will be on QH, which is usually the highest bit in the shift register. So I feed QH to D0 because this is the lowest significant bit on the data bus. On the software side, receiving the byte is quite simple. You just have to input that byte from the keyboard port, but then you have to convert the byte that you received to a key. And that keyboard byte to key subroutine does this job by translating the scan code to a character, by distinguishing between push and release. You remember there are two different codes sent between pushing a key on the keyboard and releasing that key. That subroutine also keeps track of all the meta key states like Shift, Alt, Control keys, and it is depending on the keyboard layout. So if you have a German or a US American keyboard layout, which character is represented by which scan code. There is a problem with that design because there is only one byte that is stored in that shift register storage register, and the keyboard may already send the next byte even before you have read that byte from the storage register. So there is a potential data loss. But the PS2 protocol has a mechanism against this, and this is the clock inhibit protocol. That means if the host pulls the clock line low, then the keyboard stops sending additional data. So the keyboard has its own buffer, and it buffers all the keystrokes that are done while the clock is pulled low from the host side, and the keyboard resumes sending these stored data bytes after the clock is released again. There's a second problem, and that problem is that the PS2 clock runs independent of the CPU clock, and so the CPU doesn't notice the receive operation at all. So the CPU might either pull the keyboard often, that is time consuming, or seldom, which is slow. Another thing is, if there is a byte in the storage register, is it by chance the same byte that has already been sent before, or is it the last byte that I have already read? So I can't distinguish between the same byte sent again and the same byte that I already read. That is important for automatic key repetition, like if you push the key and don't release it. The solution that I came with is an interrupt, so I set an interrupt line high as soon as there is a byte available, and the CPU then jumps to a dedicated interrupt code as soon as a byte is available and resets that interrupt line again. So whenever there's an interrupt, I know there is a new byte that I've received. These two solutions can be combined into a hardware solution that I have an RS flip-flop which contains 1 if there's an unread byte available, and this flip-flop is set after I received 11 bits. So as soon as the keyboard ends sending the byte, I set that unread byte flag. That flip-flop is reset after the output enable of the shift register is set, so I detect when data is read from the shift register, and then I reset that RS flip-flop. That way I know for sure that the byte that is received has been read from the CPU side. That RS flip-flop also sets the clock inhibit, so as long as the RS flip-flop is set, the clock line which is connected to that flip-flop is pulled down via an additional transistor, and that prevents the device from sending additional data as long as I have an unread byte set in the controller. Also, that flip-flop is connected to the interrupt request line, so the CPU is informed about that unread byte as long as the flip-flop is set, and since there is one interrupt per received byte, I can surely distinguish between the same byte or a repeated byte. That adds a transistor and an additional chip to the controller design. In the schematic you can see that flip-flop is built out of 2 NAND gates here on the right hand side, and it is triggered as soon as there are 11 bits received. This is clock count 13. That is the same signal that also resets the counter. And if that flip-flop is active, that red LED lights, and you can see that there are 2 lines activated. The first one is the interrupt request line that goes to the control logic and requests the interrupt subroutine to be engaged. And the second line goes to that transistor here that is connected to the clock line on the PS2 bus and pulls that clock line low so that the device is inhibited from sending further data. The side effect of that pulling low is that our counter is already loaded with a value of 1 at this time, because it is as soon as the clock counter reaches 13, a new load with a value of 1 is done. And if that clock inhibit gets released, which is done when the keyboard enable line is brought back low again, because this is the RC circuit that resets the flip-flop. there is another rising edge of the clock that puts the counter to value 2 even before the first bit from the device is sent. While most of the data is sent from the keyboard to the host, there are some commands that the host can send to the keyboard. These commands include things like forcing the keyboard to reset or to set the keyboard LED state. Don't know if you knew, I didn't before, that the LED lights on the keyboard are controlled from the host side, so an LED on the keyboard is not switched on or off by pushing a key directly, but the host is sending a command to switch on that LED as soon as it has received the key that is connected to that LED. Another thing that is just vice versa, so I always thought that the host is controlling how often a key is repeated as long as you have that key pushed, but in fact it is the keyboard that controls how often it sends the scan code for that key as long as it isn't released. So the keyboard speed repeat is also set as a host command. And there are some more commands. Since the clock is always driven from the device side, the host has to request a send by pulling the clock line low for at least 100 microseconds, then pull the data line low and release the clock line again. The clock itself is then generated from the client side, and the host first has to wait for the clock to be low and then start sending. I recorded sending a byte with my oscilloscope too, so what you see here is the request to send. You see the clock line is pulled low in the beginning, and right before the clock line is released, the data line is pulled low as well. The spacing between two grid lines is about 100 microseconds, so you see the clock is a bit more than 100 microseconds low and then released again. After that, the host waits for the device to operate the clock. I said before, the clock is driven by the device, and the device starts by putting the clock low, which is the start bit. Then the host starts to send its byte by issuing the least significant bit of the byte. So the host puts the least significant byte on the data line, then waits for the clock to be high and the clock to be low again. Then, if the clock is low again, the process repeats and the host issues the next bit on the bus, waiting the clock to be high and waiting for the clock to be low. That is repeated until the last bit is sent, which is the highest bit, the bit 7, so that there are 8 data bits put out on the bus, which in this case, read from back to front, is hex code ED, which is the command for set LEDs. After that, a parity bit must be sent, and it is odd parity again, so it must be an uneven number of ones, including the parity bit. And after that parity bit is sent, the client, in this case the device, sends an acknowledge in the form of the data line to be pulled low. In this case, for this to be sent, the host has to release the data line, then has to wait for the data line to get low, and then wait for clock to get low, and then for both lines to get high again. That is the acknowledge sequence from the device, so the host knows the device has seen my byte. Sending data to the PS2 bus is always synchronous, so that the CPU always knows when it sends data, and so it is possible to drive the send operation completely in software. That software needs direct write access to the clock and data line, which in turn means that I need an additional transistor to pull the data line low. Also, I need read access to the clock and data line so that I can wait for those lines to be low, which is important at certain points in time in the protocol. To store these states, I use a 4-bit register. It's the 173 register chip, and 2 of the bits are the state of the clock and data line. So as long as those bits are 1, the clock or data line are pulled low. Another bit of that register is used to stop the counter from counting so that the receive counter does not interfere with sending data. And the last bit is for the command mode switch so that I can put the whole controller in command mode. In command mode, the PS2 controller will output the state of the clock and the data line directly to the data bus and will no longer put the storage register of the shift register to the data bus so that I can read the state of the clock and the data line directly. It also outputs the receive RS flip-flop state to the data bus so that one can check whether or not there is an unread byte in the receive buffer. And that is done with this multiplexer chip. You know that 157 multiplexer. This one is the same, but it has a 3-state output, so it can directly be connected to the data bus. And so I can easily switch between a received byte and the direct access to the PS2 bus. These 2 chips and the additional transistor complete the hardware of my PS2 connector. This is the complete schematic of my PS2 controller. The central part for sending data is this 173 register chip. 2 of the bits allow direct access for write to the PS2 bus. This is for the clock, so the same transistor that is already used for the clock inhibit, for the congestion, is also used for pulling the clock low during the send, and the other bit is for the data line, so this is to pull the data line low. Another line on that register chip is the command mode line, which first switches that multiplexer so that the multiplexer delivers the data line and the clock line directly to the data bus. As soon as the keyboard enable line is set low and that command mode is set, the multiplexer is connected to the data bus and sends out the data or clock line on the data bus. Another thing that this command mode operates is the flip-flop state. So as long as the PS2 controller is in command mode, the flip-flop for unread scan data is not reset, so this makes it possible to look for received bytes, because there is another bit that is put on the bus if we are in command mode, and this is the information about a received byte. The last bit in the register is the count enable line, so the counter can be held if data is sent, so that the counter does not interfere with sending data. I could squeeze the whole hardware on a single breadboard. This is the input from the keyboard, and these are the 2 transistors for the data and clock lines to be pulled low. These four LEDs are not in the schematic. It is the current counter state, just for debugging purposes. This is the counter. And this is the NAND gate for the counter positions and the shift register. This is the NAND gate for the flip-flop. So you can see the short flickering of the red LED when data comes in. This is the multiplexer, and this is the 173 gate, which is connected to the data bus. This short code sequence in my CPU specific assembly language is enough to receive a byte from the PS2 controller because the protocol itself is handled in hardware. So this code first checks whether or not there is a byte available, and for that it switches to the command mode and reads from the keyboard port whether or not there is a byte received, and if so, that byte is taken from the keyboard port and delivered back to the caller. The code for sending data over the PS2 bus to a device from the host is more complex because the protocol is handled in software. The software starts by requesting the send. If you remember, that required the clock line to be pulled low for about, or at least 100 microseconds. This is done here. The clock is pulled low and then there is a wait for about 150 microseconds. Then the data line is pulled low as well, and the host waits for the device to pull the clock line low again. After that, the host will begin to send the byte bit by bit, so the byte is shifted out to the right because the least significant bit has to be sent first, and depending on the bit being set or not, the data is pulled low or not, and the host then waits for the device to put the clock high and then low again. This is done 8 times. There is a counter in this address, and after the 8 bits are sent, the parity bit is transmitted, and finally the host waits for the acknowledgement from the client. After freeing the clock line and the data line, the client will answer with another clock low and high again, and then the host leaves this function. At the end, I want to do a quick demo of my keyboard controller. Of course, you can type letters by hitting the keys on the keyboard and support the shift key. So if you hold down the shift key, the letters will be uppercase letters. The caps lock function is also supported. So if caps lock is active, the keys are uppercase without pressing the shift register. Some special keys are also supported. This is the backspace key, and the completely useless scroll lock is also in my list. To see the congestion prevention, I stop the IRQ, and you see that red LED shows there is an received byte that is not taken yet. And yeah, Control Alt Delete is also supported, so there's a reset. Okay, that concludes my video. Thanks for watching. As always, feel free to comment and hope to see you soon. Bye.